Hello everyone, I welcome you all in today's presentation. Today we intend to solve few numerical problems on the design of connecting rod that we have discussed in previous presentations. As we all know that design of connecting rod primarily involves determination of the cross section of the connecting rod, length and diameter of small end bearing, length and diameter of big end or crank pin, dimensions of big end cap and bolts, and finally we need to check for the whipping stresses. Before moving further, I would request the students to go through the presentation slides of design of connecting rod so that you'll be able to understand the procedure in a better way and you yourself will be able to solve the numericals. Let us move on to the numericals. We will try to take various questions on connecting rod that involves determination of all these design parameters. Here comes the very first and basic question. In this question, we are required to find the dimensions of cross section of the rod for the given cylinder bore of 100 mm, length of rod as 320 mm, maximum gas pressure as 2.45 megapascal, and factor of safety against buckling failure as 5. We know very well that the force on cutting rod PC is given by pi by 4 d square into P max. Since d is given to us and P max is also given to us, putting the values we can find PC as 19242.2 newtons. Now we all know that we design a connecting rod treating it as a column and we use formula for the same, and that is Rankine formula. Rankine formula, we find crippling load. So we'll multiply the force that is coming onto the rod by a factor of safety that is given in the question as 5. That means whatever load is coming on the connecting rod, we'll multiply that by 5 to find the crippling load. So crippling load comes out to be 96,211.3 newtons. This is the very famous Rankine formula. This is the formula. Now we know that I section is the most appropriate cross section for a connecting rod. We have discussed the reason behind it also. For a connecting rod to be equally strong in buckling about XX and YY axis, moment of inertia about XX axis should be 4 times moment of inertia for YY axis. And I section is the only section where IXX is 3.2 times IYY for these dimensions. That is, this height as 5t, this width as 4t, and this thickness of web of length as t. So we'll assume this as a standard cross section. So here we need to find the value of t. So sigma c is not given to us. We'll assume its value for steel as 330 megapascal. A is the area. Area for this cross section is 11t square. We can find the same considering it as 3 rectangles. A is a constant, Rankine constant, whose value for steel as is 1 upon 7500, and kxx for this section is 1.78 T, and we have already found our crippling load. So in this equation, only unknown left is T. Putting all the values, we can find the value of T. So we'll be able to find what is 5T, what is 4T, and what is this thickness of web and flange. So this was the basic numerical in which we have found the dimensions of cross section. Invariably, in every design question, we are required to find this dimension. Let us move on to the next question. In this question, we are supposed to find the dimensions of small and big end bearings. That is, the length and diameter of small end bearing, which is also called as piston pin, and length and diameter of big end bearing, which is also called as crank pin. And the data are given to us. Here we are fortunate that L/D ratio for piston pin and crank pin bearing is given to us, and bearing pressure is also given to us. If they are not given in the question, we are supposed to assume the same, and in that, data book will be of great help. Let us try to solve this question. We know that piston pin and crank pin are designed for the maximum force coming onto the connecting rod PC by 4 d square into P max. For the values of cylinder bore and P max, the value of PC comes out to be 19242.2 Newton. Now, this is the piston pin, and we are supposed to find the length of pin and diameter of pin. We know jolly well that the force acting on the piston pin is given by PC equals to, this is bearing area, budgeted area, dP into LP into bearing pressure for piston pin. Putting the values of PC and as given LP by dP as 1.5, so LP will be 1.5 dP, and bearing pressure for the piston pin is 15 megapascal. So only unknown left in this equation is dP. dP square comes out to be 855.21, or dP is 29.24 mm, say 30 mm. Since LP is 1.5 of dP, so LP will be 45 mm, which is the desired dimensions of small end bearing. On the similarly, we can find the dimensions of big end bearing also. This is the length of big end bearing, and this is diameter. So PC is given by DC into LC, which is the projected area of big end bearing, and PPC is the permissible bearing pressure for crank pin bearing. So putting all the values and LC as 1.4 times DC, the ratio of L by D for big end bearing, which is given as 1.4. Putting all the values, DC square comes out to be this value, or DC is 37.07, say 38 mm. Since LC is 1.4 times DC, so it is 53.2 mm, or we can say 54 mm. So you will see that once the approach is clear to us, we can very well apply the same to solve numericals. In the two numericals that we've discussed till now, in one numerical we found the dimensions of cross section, and in the other numerical we found dimensions of small and big end bearings. Let us move on to the next. In this question, we are supposed to find the diameter of big end holes and thickness of cap for the big end. We all know that big end is made in two parts, and the cap is fastened to the big end with the help of two bolts. When we've discussed the design portion, we found that the big end bolts and cap are subjected to the inertia forces, which is given by this formula. Mr omega square r cos theta plus cos 2 theta over n1, where Mr is mass of reciprocating parts, which is given to us as 1.75 kilogram. Omega is angular speed. Since n is given to us, we can find the same. R is crank radius. We are given length of crank pin, so R will be half of this. Theta is the angle between crank and the line of stroke, and N1 is the ratio of length of connecting rod to the crank radius, which is also known to us. Since length is known to us and we have found length of rod is known to us, which is 320 mm, and this length of stroke is 140 mm. So R will be 70 mm. The inertia force will be maximum for theta value 0. So Pi max will be Mr omega square R 1 plus 1 upon N1. So R is stroke upon 2, 70 mm. Omega is 2 pi by 60, 157 radians per second. And N1 is L by R, which is 320 length of rod upon 70 crank radius. Comes out to be 4.57. And Mr mass of reciprocating parts is given as 1.75 kilogram. Putting all the values, the value of inertia force, maximum inertia force, comes out to be 3683.9 newtons. Now we need to design. As shown in this diagram, the bolts are subjected to tensile forces. Since there are two bolts, each bolt will share the maximum inertia force equally, which is given by this equation. So Pi max will be 2 is number of bolt. Area 1 bolt is pi dc square by 4. This is permissible stress for bolt material. Putting the value of Pi max and sigma t, the only unknown left in this equation is dc, which is core diameter of bolt. dc comes out to be 4.42 mm, and we know that nominal dia d is given by dc upon 0.8. So D comes out to be 5.53 mm, or we can say 6 mm is the required diameter of big end bolts. Now we are supposed to find the thickness of cap for big end. We know the big end cap is treated as a beam that is freely supported at the bolt centers and loaded in such a way that it is between uniformly distributed and centrally considered load, and the bending moment in such a scenario is given by MB as Pi max into L over 6, where this is the load Pi max, this is length L, which is between two bolt centers. We can find this L from this formula, where DC is diameter of crank pin, which is crank pin somewhere over here, which is given to us as 38 mm, plus thickness of bush, 3 mm bush over here and 3 mm bush over here. So twice thickness of bush plus diameter of bolt. This is radius of bolt, this is radius of bolt. So together they combine diameter of bolt plus clearance somewhere over here of 3 mm. So length comes out to be 53 mm. Putting the value of Pi max and length in this formula, bending moment comes out to be 32541.8 Newton millimeter. Now, since we have decided that we will design it treating it as a beam, so we'll use the formula sigma b as mby upon I, where I is BC TC cube over 12. BC is width of cap, TC is thickness of cap. A little consideration will show that BC will be equal to length of crank pin which is given to us. So y is Tc by 2, I is this value. When we keep all the values in this formula and putting sigma b as 120 megapascal, the only unknown left in this equation is Tc, that is thickness of cap, which is required dimension. So putting all the values, thickness of cap Tc comes out to be 5.49 mm, or we can say 6 mm. So in this question, we were required to find the diameter of big end bolts and thickness of big end cap, and using the approach that we have learned in our design of connecting rod, we can easily find the required parameters. We all know that there is one more concept left in design of connecting rod, and that is of whipping stress. So let us discuss one question on whipping stress. In this question, we are supposed to find the whipping stress induced in the connecting rod. We know that whipping action induces bending stress in the connecting rod, and the bending stress is induced due to whipping action is called as whipping stress. Whipping action is due to the fact that small end of the connecting rod is having pure translation motion, and big end of the bearing is having pure rotational motion. So intermediate points will have different bending moments, which tends to provide the thrust on the connecting rod, and as a result bending stresses will be induced, which are called as whipping stresses. We have learned that magnitude of maximum bending moment for whipping action is given by this equation, where m1 is the uh, it is omega square r l square by 9 root 3. m1 is mass of connecting rod per unit length, and to find the same we have been given density of material, connecting rod material, and area for the standard cross section we know as 11t square. So m1, which is mass of connecting rod per unit length, comes out to be 3.1 kilogram per meter. L is length of connecting rod, which is given to us as 320 mm. R, crank radius, is length of stroke 140 upon 2, that is 70 mm, and omega as 157 radian per second. So m1 is known to us, omega square we found, r we found, L is given to us. We can find what will be mb max. It is given by mb max will come out to be 35.17 Newton meter. For this standard cross section, the whipping stress shall be calculated by the formula sigma b as mby over ixx. For the standard section, ixx is given by this equation and y is given by 5t by 2. When we put all the values, value of mb, y and ixx, the whipping stress comes out to be 11.66 megapascal, which is well below the permissible limits. So we can say that apart from determination of whipping stress, we can also comment on that this connecting rod is safe in whipping stress also, as the stresses induced due to whipping action are well below the permissible limits. Now there is another question that has came in the RTO examinations held in 1718, just to make sure that whatever we have learned, the same we can apply to solve this question, and whatever we are doing, we are on track. So if we are able to solve the numericals that we have done in previous slides, and we have able to understand what we have done, we can easily attempt the question like the one given or came in the university examinations. We'll not solve this question, but rather we'll discuss the steps involved. I would like you to solve this question so that you'll feel confident that yes, you can attempt the questions of design of connecting rod. Here you can find that we are supposed to design a rod completely. That means we are supposed to find the thickness of cross section, then small and big end bearing, diameter and length, then big end bolts, big end cap, and also we should check it for the whipping stresses. Here one line has been mentioned that assume suitable data and state the assumptions you make. You can see to be able to find or to be able to design the rod completely, lots of data are missing and the same are need to be assumed with the help of data book or with the help of common values that you remember from previous questions. So let us discuss it in steps, and as we have decided that I would like that you solve this question at your own. So step 1 would be assuming I section as standard cross section, will calculate T. Like we have done in the numerical first, we used the Rankine formula in which crippling load is to be put. So crippling load will be found by multiplying the maximum force on the connecting rod with one FOS, which is not given. So we'll assume the value as 5. And for finding PC, that is pi by 4 d square into P max, d is given to us 125 mm and P max is given to us 3.5 megapascal. So from this values we'll find PC. We'll multiply PC by 5 to get the crippling load. Put the same in the Rankine formula, and we need to assume this compressive stress also. Assuming the material is steel, the stress will be 330 megapascal, and this Rankine constant for steel is 1 upon 7500. So putting all these values in the Rankine formula, we'll be able to find the thickness. We'll design big and small end bearing. We'll assume L by D for big end bearing as 1.4 and bearing pressure as 10 megapascal. Similarly, we'll assume L by D for small end bearing as 1.5 and bearing pressure as 15 megapascal. We have done the same in question number 2 also in this presentation. So you should work on the same lines to find the dimensions, that is length and diameter of small and big end bearing. Then we'll design big end bolts and thickness of big end cap considering maximum inertia forces. We'll assume permissible stress for bolt and cap material from the design data book. And in the last, we'll calculate whipping stress and check whether the same is within permissible limits or not. To be safe, the whipping stress should come out to be less than 50 megapascal as a general guideline. So in this small presentation, we have tried to solve a variety of numericals that pertains to design of connecting rod. I am sure that if we understand the design procedure and we are familiar with the steps involved in design of connecting rod, we'll be able to solve the numericals in this presentation and many more like this without much difficulty. We'll meet again with some other topic in the next presentation. I hope you the presentation and we'll practice more and more numericals on the topic of design of connecting rod and other topics also that we have covered in our previous presentations. Thanking you all for your patient hearing.